Kia ora Year 12 and Year 11. This video is going to go through the basics of how to find the equation from what you see in the graph for exponential graphs. My focus is going to be on the equations out of context, but remember we're usually more interested in using these skills in context. So make sure that you do lots of practice on that as well. Okay, here comes the first one. Right, this is my basic exponential graph, so I want to have a look at some of the features of it before we start moving it around and reflecting it and stuff. Things to notice here are it's got an asymptote. So there's a value that it never ever touches, and it can never get as low as 0. Alright, so the asymptote is at y equals 0. And the pattern here, well, we can see we've got exponential growth, but things to notice, we've got this key point here is 0, 1. That's happening because the exponential graph has this for its basic form, some number to the power of x. And in this one, the points that we've got are 0 and 1, 1 and 2, 2 and 4. So these look like the powers of 2. And that's the giveaway that this is the graph of y equals 2 to the power of x. So just to go over this point here again, because this is really useful in working out the equation, 2 to the power of 0 is equal to 1. So if you find this pivot point here on an exponential graph, it's telling you that you probably have a reasonably straightforward transformation of the basic form. Okay, so now we're going to start transforming them a bit. So this one here looks like it's been shoved down, and it has. If we think about the most general form of an exponential graph, it's this. And just as in our easier graph patterns, this plus c term is looking at a vertical translation. So in this case we can see that the asymptote is at y equals -4. And that is my clue that this is an exponential graph that's been translated down 4. So what do we do next? Well, that means we're going to try figuring out this pattern here. The reason I suspect that it's a reasonably simple one is that this pivot point here, which used to be at 1, is still just shifted down 4. So the easiest way to do this is to look at some values. So we've got x is 0 and y is -3. X is 1 and y is -1. And x is 2 and y is 5. Now what we can do is pop the 4 back on to help us spot the pattern. So we're going to add 4 to each of those y values and see if we recognise something. So 3 plus 4, -3 plus 4 is 1, -1 plus 4 is 3, and 5 plus 4 is 9. So this is telling me that my base is 3. So the equation here is y equals 3 to the power of x minus 4. Okay, so our basic form is 3 to the power of x, and this graph has been translated down 4 units. Next one. Right, well this looks like an upside down exponential. So it started off like that and then it got reflected in the x-axis. So we're going to try this for the form of the equation. Okay, so all of the y values have become negative. It's still going through a pivot point that is -1. So we'll take a look at the points and we get x and y. Well, when x is 0, y is -1. When x is 1, y is -2. That's that one there. And then this one here, when x is 2, y is -4. So you can see I've got 2 to the power of something going on there, with a negative sign in front of it. So this one is y equals -2 to the power of x. This negative sign is telling me that it has been reflected in the line y equals 0. Okay, next one. Right, this is a different reflection. This is my basic graph. This is what I've got. So, if we're doing a reflection in the y-axis, when we have an exponential graph, that is coming through by having negative exponents. So let's have a bit more look at how that's happening. We'll put in some points. So let's find these blobby points. We'll start with h. So when x is negative 3, y is 8. When x is negative 2, y is 4. And when x is negative 1, y is 2. And happily, when x is 0, y is 1. So the pattern here is that y is equal to, well, we've got powers of 2 here, so we're going to have 2 to the power of negative x. Now if that's confusing you, just let's take a look here and substitute in negative 3 here. So when x is negative 3, 2 to the power of negative 3 is equal to 2 cubed, which is 8. Okay, so that's the equation there. So when we're reflecting in the y-axis, we will have this functional form. Alright, now in the last slide we did this for the equation. We had y equals 2 to the negative x. I could also have modelled that equation as equaling, well, 2 to the negative x is the same as 2 to the negative 1 to the power of x. Now 2 to the negative 1 is 1/2 to the power of x. So this is one of the cool things about exponential equations, is that I can write them in two different ways. I can write them with a negative power, which happens when I'm thinking about reflection, or I can write them as having a fraction as the base. And that's the pattern we're usually going to see when we're doing exponentials that are heading downwards as x gets bigger. And that's how I'm going to approach this one. So I have got these values of x and y. I've got x 0, y is 1. X is 1 and y is 0.8, and x is 4, y is 0.41. So I've got y is equal to k to the x, and I need to figure out what k is. So I can substitute in 0.8 is equal to k to the power of 1, so k is equal to 0.8. So it looks here like y is equal to 0.8 to the x is my equation. So let's substitute in 0.8 to the power of 4, and you'll see that we get 0.4096, which is 0.41 to 2 dp. So that's looking pretty good. So this is a simple one. Again, this is not in context. So the thing we've got going on here that makes it easy is we're still going through 1 when x equals 0. Okay, so we've got that pivot point. In the questions you've done in class, we usually won't be going through 1. We'll be going through something else related to the temperature or the money or whatever kind of problem we're solving. Okay, here comes another one. Let's see what's happening here. Well, we've got y, now it's going through 1 again, so it's going to be k to the power of x. Right, and now we can shove a point into it, substitute a point into it. We get 0.1225 is equal to k squared. Right, so we can solve that by taking square roots of both sides. And let's see what we get for that one. So the square root of 0.1225 is 0.35. Okay, so now here we have y is equal to 0.35 to the x. Now let's just think while we're here about what that means. This means y is equal to 1 minus 0.65 x. So every time period or every change in x, we are reducing our current value by 65%. Okay, just as if we had y equals 1.5 35x to the power of x. That would be increasing by 35% per time period. Okay, one last one to look at coming up. Right, the first thing to notice here is that this is different because it goes through 2 when x is 0. So the form here is not quite the basic form. It's going to have a stretch factor in it, and we're going to look at some blobby points here. So the first one to notice is that when x is 0, y is 2. So that is telling me something. So the next point will be 1 and 6. So we're trying to solve this equation. Now I know this is the form of the equation because my asymptote's still at 0, so it hasn't been shifted up. So in this case, we're going to substitute in and we get 2 is equal to a times k to the power of 0, a equals 2. So the equation is y equals 2 times k to the power of x. So if I come over to my little table and I divide each of those y values, it's easy to find the base, right? It's going up in powers of 3, 1 and then 3. So this equation will be y is equal to 2 times 3 to the power of x. Okay, that's all for now. The only kind of transformation I haven't done in here is when we're shifting left and right. So when I'm translating left and right. And you see those in this pattern. So if I wanted to translate 3 to the power of x right 5 units, it would become y equals 3 to the power of x minus 5. Okay, but I just didn't have any examples handy of that kind, so make sure you've gone over those in your new late book. Alright, thanks for watching. I know that was long. Hopefully that helped a little bit.